Okay, so we're going to start talking about angular momentum. Before we go into what angular momentum is, we need to take care of a few things, which is namely understand the cross product of vectors. Now, we have come across this cross product of vectors when we studied simply rotational motion, and when we saw that there was an omega and there was a v and an r, and without really saying a lot, what we actually had is that the velocity v was equal to r cross omega. Okay, and we'll explore this a little bit more and we'll understand what we have. There are other quantities also that we have, which is also the fact that the torque tau, which we're going to use a lot, is equal to r cross f. So let's first, before we do all these things and we start making connections with all these things, let us just quickly introduce what cross product of vectors is and see where to go from there. Okay, this cross product of vectors is also called the vector product, because when you cross a vector, one vector with another, you end up getting in vector quantity, okay, as opposed to a scalar product, which the dot product was. If you remember the dot product, where a dot b ended up giving you a scalar c, and unlike that, this thing gives you a vector product. So let us take a vector a and a vector b, and the way we define is the cross product is that a cross b is equal to the magnitude of a times the magnitude of b times the sine of angle theta between the two, multiplied by some vector n. Okay, so let us understand what this vector n, what the direction of this vector n is. So let's say that you have a plane, okay, and let us say you have a vector a, and let's say that you have another vector b. Okay, then let's say a and b lie in the plane formed by this little disk. Then what we have is that a cross b, and by the way, they don't have to be the same length. Let me just make sure that I draw b longer. I just want to do the disk so that you would realize that it's a plane, and the cross product of a and b is a vector that points, okay, perpendicular to the plane. So this is the direction of n. N hat is nothing but a unit vector. It is the direction of the vector a cross b. It's a unit vector in that direction. Okay, let me not even write n hat there. So a cross b is the vector that points in a direction perpendicular to the plane formed by a and b. So that's an important property of a cross product. Okay, and we'll show also a little rigorously that this ends up coming from the algebra. So a cross b, okay, is always perpendicular to the a plane formed by a and the plane formed by b. Okay, now on the other hand, if we had the same vectors, okay, so let's say I have b here and then I have a here, okay, then b cross a would be a vector that points opposite the vector a cross b. So b cross a would be pointing in this direction. So basically you're going to use the right hand screw rule, like make sure that your fingers are aligned in the direction of a, and then when you curl them into b, the direction of your thumb gives you the direction of the vector a cross b, and you do the same thing, you align your fingers with b, okay, and then you curl them into a, and then you end up getting b cross a, so which points downward. Alright, so now that we have a basic definition that a and that a cross b is equal to ab times sine of theta multiplied by the unit vector pointing in the correct direction, okay, let us explore some simple concepts here. Okay, if we were to look at the vectors I, j, k, okay, I hat dot I hat, you see, are parallel with each other. Okay, in fact, let's go back here and let us understand a couple things here. Since a cross b is equal to ab sine theta, let me rewrite this here. Since a cross b is equal to ab sine theta times n hat, this clearly tells us that if a is parallel with b, okay, then a cross B is equal to 0. So unlike the dot product, in the dot product, if it was perpendicular, if two vectors were perpendicular with each other, then the dot product would be equal to 0. Okay, but here it's the opposite. And if A is perpendicular with B, then A cross B is simply equal to A times B. Okay, so we have that. Okay, because the sine of theta ends up being, so let me put an absolute value sign here. So absolute value of A cross B is simply equal to AB. Okay, great. Now this allows us to come up with an expression in terms of the components of a vector for A cross B. Okay, so let us understand how to do that. So let's say if I have vector I, what we know now is I dot I has to be 0. So does J dot J, and so does K dot, what am I doing? I cross I, J cross J, K cross K. Okay, these are all equal to 0. Okay, now on the other hand, let's understand what I cross J is going to be equal to. Now I cross J, okay, is according to a right-handed system of coordinates. So this is X, this is Y, then Z comes out here. Okay, then if you see I, let's look at the vector I. Say I is here, J is here, and then K is here. Okay, so when you rotate I into J, you end up getting, when you rotate I into J, you end up getting the vector K. Okay, on the other hand, when you rotate J into K, okay, once again, if you look at the right-handed system, J into K, J cross K ends up giving you I, and then K cross I ends up giving you J. So these are your three things. Okay, on the other hand, J cross I, okay, ends up giving you negative K. K cross J ends up giving you negative I, and I cross K ends up giving you negative J. Now we're going to use this, alright, to find the cross product of two vectors in terms of its components. So let us say that A, vector A, is equal to AX I hat plus AY J hat plus AZ K hat. B is equal to BX I hat plus BY J hat plus BZ K hat. Okay, now when we do A cross B, what we end up getting is we get AX I hat plus AY J hat plus AZ K hat cross BX I hat plus BY J hat plus BZ K hat. Now this ends up becoming AX times BX. Okay, so let's multiply the coefficients, but then I have to I cross I, okay, plus AX times BY times I cross J plus AX times BZ times I cross K. Okay, so we take care of all the I terms here. Now let's do the same to the J term here. So the next one is AY BX times J cross I plus AY BY times J cross J plus AY BZ times J cross K. Alright, okay, one more row, and then we have AZ K hat, AZ BX K hat cross I hat plus AZ BY K hat cross J hat plus AZ BZ K hat cross K hat. Now if you look at the terms here, okay, a lot of familiar things come out. Okay, first of all, what we know is that this is 0, I cross I, J cross J is 0, and K cross K is 0. Okay, then we know that I cross J is K. Then j cross I is minus k. Okay, so we have this. Then we know that k cross I here is equal to positive j, and that I cross k is negative j. Then we also know that j cross k is equal to positive I, and that k cross j is negative I. Great. So now we have all our components, and all we need to do is put them together. So let's first put the I components together. Okay, the x component together, and that gives us ay bz minus az by times I hat. Okay, then let's do the same for the j component, and I get az bx minus ax bz times j plus the last terms is going to be ax times by minus ay times bx times k hat. Okay, so we have our entire product here. So this is nothing but the product of A cross B. Now here's another thing that we keep in mind. If you look at this product, okay, we can write this product actually in a nicer, neater form by using determinants. Okay, and in determinant form, this is nothing but we have I hat, j hat, and k hat that goes here. Then I have ax, ay, az in the next line, and then I have bx, by, and bz in the third line. So this cross product is actually equal to the determinant given by this formula. Alright, so this is it for simply just giving you a foundation of cross product of vectors. We can apply this to a few simple problems, just figuring out what the cross products are, and then we can take it from there. Okay, alright.